Yeah. All right, thank you to the brave souls who are enduring another talk of cryptography this early in the morning. Doesn't quite seem fair, but you're doing great, you troopers. The keynote was great, talking about some history with cryptography, and today I want to talk about. We're going to discuss very briefly asymmetric versus symmetric encryption. We're going to talk about it from a math standpoint, which is a little bit different. Mike, stop smiling at me. You said you're going to make faces. And then we're going to walk through an actual example of how asymmetric encryption works. For this illustration, we're going to use RSA, and then we're going to step through the algorithm one step at a time so that you can understand the theory behind it. And then to finish off, I'll talk about some of the subtle differences between the way that we are calculating this manually, encrypting and decrypting it manually, versus how your computer actually does it. So if you think back to algebra, you have to keep things balanced on the same side. So if I say -5 on one side, I'm going to have to do the same thing on the other side. And then if I want to reverse that process, I subtracted 5, and then I'm going to have to add 5 to get back to where I was. So you can see how data, with numbers, we can use the inverse to come back full circle. And we can do the same thing with text when you represent text as numerical values. And this picture kind of illustrates that. So if you guys were like me in middle school, you're writing messages to your friends, but if it's secret, you have to encode it some sort of way. And so if you ever did like Caesar cipher or things like that, you tell your friend the key, or you come up with other little secret languages. So you can see that there are many kinds of ways you can permutate data to change it. Here's some complementary functions. So if you add, in our example earlier, if you add 5 or subtract 5, you can do the inverse to get back to where you were. Same with division to multiplication. If you sin, you repent. Matrix multiplication doesn't actually, there's no such thing as matrix division, so it's called inverse matrix multiplication, and that will bring it back to where you were. So it works for simple functions, it works for trigonometric functions. Symmetric encryption is really great and all, but it gets messy because it doesn't scale well. Because if the person in the middle wants to send encrypted messages with symmetric encryption to each of the people here, they're going to have to distribute keys. But then they've got to keep track of a key per person that they're communicating with, so you can see how it can quickly get really ugly. By contrast, with asymmetric encryption, it's more like handing out locks. So you hand out your public key, that's what's represented by the lock, and then the key in this picture represents the private key. So they basically lock up the message, send it to you, and then you have just that one key that you can use to decrypt all those messages. The benefits are that it's much simpler. The downside is that it's a lot slower. It's more computationally expensive, but you can justify that difficulty because it is based on more complex theoretical results. So asymmetric encryption is used all over the place. You can see this is something we use every day. And we'll talk about that a little bit more later. A brief introduction into the RSA Cryptosystem. The acronym RSA comes from the last names of its 3 inventors who were studying at MIT and doing research. Actually, there was a guy named Clifford Cox. He worked for a British intelligence agency, and he came up with the same idea in 1973, but no one knew about it because it was kept secret until, I want to say, like 10 or 15 years later. So kind of cool. All these people were coming up with some brilliant ideas on how to make asymmetric encryption work, where you've got different keys and yet you're able to still do that inverse function process that we talked about to get your data back to where it was and be able to transmit it securely. So we're going to go through an example, and this is going to be very simple. So back to middle school, the message I'm sending to my friend is B. I don't know if I'm cheating for a test or something. Don't cheat, kids. But B is the message. We're going to keep it really simple, and we're going to represent it with the number 2. If you say A is 1, B is 2, C is 3. We're going to say B is 2 because once it's numerical, we can start doing mathematical functions on it. So here's our message. It's going to be represented by M, and this formula, C equals M to the power of E mod N, is the RSA formula to encrypt. When we treat plain text as our message as a large binary number, if our message is actually bigger than our N, you have to break it up into smaller pieces, into smaller chunks to encrypt and then send piecemeal. The suggestion is to break it up by the largest power of 2 that's still smaller than N. If you want a fancy term to add to your vocabulary, we call that modular exponentiation. So that's cute. All right, so we're going to plug in 2 for our message there. And then here's our public key. So 5 and 14 are the 2 values that comprise our public key. And this is the public key that was represented by the lock in the picture earlier. So the 14 is our N value, and E stands for like our encryption key is 5. So we're going to plug those numbers into our formula there. We have 2 to the 5 mod 14. 2 to the 5 is 32. And 14 modulus is basically the remainder. If you remember doing math in 4th grade, you divide a number however many times it goes evenly, and then you have some leftover numbers that become the decimal or your remainder. So 14 goes into 32 cleanly twice, gives us 28. The leftover is 4. So we've successfully encrypted our message of B into 4, which will represent the letter D, because it's the 4th letter. So that is the message that will be sent across the wire. My friend gets it. You can be my friends today. So you get it, and the letters D, you're going to change that into 4, so you can start running your calculations on it. Here's the formula for decryption. C to the power of D mod N. It is different than the encryption formula, so that's why we call it asymmetric. So we're going to plug in our numbers. C stands for ciphertext, so that's 4. And here's our private key. The N, the 14, is the same N that was represented in the public key. And then the D is the decryption key. So we're going to plug those numbers in. 4 to the power of 11 mod 14. And obviously everyone knows 4 to the power of 11 is 4,194,304. So then we're going to mod 14 on that, longhand of course, because that's most fun. And you get 2. You can check me on the math, it does work out. So we get it back to B, which was our original message. So we can see that's how it works. Maybe you're thinking, that was really cute and fun, Shelby, but how did that work? So how did you know to use the key 11, right? So let's talk about how to actually generate those keys and know that those numbers are going to work out. So to start off, you're going to pick 2 prime numbers. These are represented by P and Q, and they're randomly chosen. Obviously, I'm using very small numbers here, but in the actual implementation, your numbers are going to be a lot larger. And these prime numbers, I believe, can also be pseudo-prime because computationally speaking, it's going to be very difficult to brute force it, even using pseudo-primes. So we've got our P and our Q. And our next step is we have to calculate N. This is the N that was published with the public key as well as used for the private key. So our value is going to be 14. The N is called the modulus. It's also called the trapdoor because it's a one-way function. Not in the sense that it can't be undone, but it's not feasible to brute force it. Once you start getting into really big numbers, I mean, these N's are usually, what is it, the 2048 key. So these N's are usually a lot bigger than what you can just brute force. So for that reason, we call it the trapdoor because it's easy to do our P times our Q, but it's very difficult to come back. And because of this is the magic of the RSA crypto system, because of prime factorization, it's going to be easy to calculate it in one direction, but nearly impossible to break the encryption by reversing it. Also, another fun vocabulary word for you is semi-prime. N is considered a semi-prime number because it's made of 2 primes. So that's fun. Okay, our next step for figuring out our system is we have to get 5n. And so we're going to start by listing our numbers 1 through n. N was 14. So here are all our numbers. And then we're going to cross out every number that has a factor in common with n. So n is divisible by 2, by 7, by itself, and by 1. We're actually going to give 1 a special pass because it makes the math work out. 1s and 0s are usually just kind of special when it comes to math. So except for 1, we're going to cross out all of the numbers that have a factor in common with n. And so you see we're left with 1, 3, 5, 9, 11, and 13. So phi n is the phi function is actually a count of the number of coprimes, which is the numbers that are not crossed out. So we've got 6 in this case: 1, 3, 5, 9, 11, and 13. So phi is going to be, phi n is 6. And I didn't define coprime. Coprime means that they don't share any common factors. So if you don't want to actually write down every single number all the way up to n, which is going to be a very large number, there's actually a quicker way to do this. This is called the Euler-Totient function, and it makes it a lot quicker for us there. We get the same result. So we'll go back to where we were in the process, and our next step is to choose an E. So E is a little bit finicky. So E, it has a couple conditions that's going to tell you what you can use for E. The first is that it has to be between 1 and phi n. In this case, phi n was 6, so our options are 2, 3, 4, and 5. The next condition is that E needs to be coprime with n and phi n. So I wrote down all the coprimes. We already figured out the coprimes of n from our previous slide where we crossed out the numbers. And then coprimes of 6 are just going to be 1 and 5. So the only option we have that fits all 3 of these, or all of these conditions, is 5. That's the only one common here. See, it's listed with all the chevron points. So our E is 5. Okay? Does anyone have any questions? Is this boring? You good? Okay, cool. Our last step is to find a D, and D can actually have several options, and we're gonna solve this one backwards. So if you look at this formula, DE mod phi n has to equal 1. So we're gonna solve backwards for D. We're gonna plug in our numbers that we have. So 5D mod 6 has to equal 1. So what are our options? Well, if D is going to be multiplied by 5, we only have options that are multiples of 5. So our options are 5, 10, 15, 20, 25, and so on. And so you have to, if we run a mod 6 on each of these, we're going to keep going through that until we get one that is where mod 6 equals 1. So if you start with, there's kind of a walk through this mental process with me. If you start with 5, so say D is 1, if you mod 6 on that, it equals 5. 5 doesn't equal 1. If you go up to the next increment, if you say D is 2, which means that we have 5 times 2, so 10 mod 6, we're going to get 4. The next one, if you move to 15, it's going to be 3. If you move to 20, it's 2. And then it goes on. So actually, you get this repeating pattern. So every, in this case, it's mod 6. So every 6 integer is going to be an option that you can choose for D. And they're all going to actually work out. In this case, I chose D equals 11. And there are, later on I'll show you in real world implementations, there are limits on what kind of a D you should choose because you have all these options and you shouldn't pick one that's too big because it's just kind of messy. So we have all the pieces of our crypto system. We figured out our public key and our private key. And the amazing thing about RSA is that the public key is published, and it includes the N, it includes the encryption key, and the entire algorithm of the whole crypto system for RSA is publicly known, and yet it still works as long as you keep your D, P, Q, and your phi N secret. So does that make sense how that works because of the prime factorization? Awesome. Okay, so there are a couple differences between the way that we calculated it and the way your computer's actually going to do it. So when we were talking about the lengths of P and Q, these should be chosen at random, and as we know, when it comes to security, finding true randomness is difficult, but we are not going to get into that today. For finding prime integers, the more efficient way to do this is using a primality test. And your P and your Q should be different lengths of number of bits, but pretty similar, like close to each other. And then we know about the N. We've talked about that. When we talk about the key length, it's actually the length of N. So NIST recommends at least 2048 bits, although you can increase it if you want. Keep in mind that increasing it is going to lower the speed of your implementation. Okay, number 3 is pretty different. We actually didn't even talk about lambda functions when we did our walkthrough. But this function that I wrote out on step 3, that's called Carmichael's totient function, and the LCM stands for least common multiple. This works out because it does boil down essentially to Euler's totient function, which is what we used, which is the P minus 1 times Q minus 1. The reason it works is because phi n is always going to be divisible by lambda n. So if you want to get more into this, which you probably don't, but there's a theory that kind of proves this. It's called Lagrange's theorem. And you can apply it to the multiplicative group of integers modulo PQ. So basically, a simpler way of doing it. In the original paper published by the RSA inventors, they did use the Euler totient function, but with the lambda function, it's going to be more efficient to calculate. And there's a Chinese remainder theorem that also goes to prove that and helps solidify that as well. Let's see, we talked about choosing E, and there are all these different rules that apply. Similar rules. We used our rules for E based on phi of n, but the same rules apply with lambda n as well. The last step is the modular multiplicative inverse, so your D. When the original writers made RSA, they actually published it with steps 4 and 5 flipped. So the way I have it written has how we do it now. They actually reversed it in their original proposal. The reason we switched it to this, to do E first and then D, is because of it's just more efficient. E is going to be smaller, and so it's going to have a short bit length and a small Hamming weight, which is the number of non-zeros in a string. So somehow that makes it better and more efficient. And then how do we use RSA in real life? It's actually really slow, so you're not going to be sending user data with RSA. It's too much overhead, too much effort. And DES is a symmetric encryption. So I mentioned that when you increase the key size, the implementation is slower. It's not even linear. So if you double the key size, if you go from 2048 to 5096, it's actually slowing it down by 6 to 7 times every time you double that key. And then we also use RSA to pass encrypted shared keys. So this is where it really shines. And so you want to do symmetric encryption for speed's sake. But in order to get that to work, you have to be able to share those keys in a secure way where they're not going to be intercepted, and that's what you use RSA for. So you're going to encrypt your symmetric key and then send that so that you can then do bulk encryption, decryption operations much quicker. So that's used whenever you're doing SSL sessions for authentication and sending the key, so that you can prove that you are the sender is who they say they are, because they're the only one who has their private key. They're also used for digital certs, which are used to prove authenticity. So you can sign your messages or the file. Even better, it's best to sign the cryptographic hash of the message, because then you're just doing it on a small piece instead of the entire file. And that basically makes it almost impossible for non-repudiation. We also use RSA for authenticating with SSH, with your login keys. And so RSA is a very good part of our lives. And that's all I have. Does anybody have questions? Was it fun? No one threw anything, so thanks. Enjoy the rest of the con.